In this tutorial, we will look at how to use op-amp circuits, simple op-amp circuits, to design basic filters. And for our filter design, we have been using the components that are shown on our exam sheet in here, which are these four op-amp combinations that give us some frequency response. The left-hand side ones are based on the inverting amplifier design, and the right-hand ones on the non-inverting amplifier design. If we look at the left-hand ones, we can see the first one blocks DC signals with capacitor 1. So low-frequency signals cannot pass. And then once we reach a critical frequency, which is this pole right in here, the C1s cancel and the J omegas cancel, and the gain just becomes minus R2 over R1. Right? And so this has a high-pass type response. And if we sketch the Bode response of the circuit next to it, see that it'll look something like this. The overall gain in here will be R2 over R1 expressed in dB, and then we have a corner frequency, which is set by this pole, 1 over R1 C1. Now the circuit below, when the frequency is high, capacitor C2 shorts out, and the output starts to become equal to the potential at the negative terminal of the op-amp, which through the virtual short will be at ground potential. So at high frequencies, this particular design attenuates, and we can see that in the transfer function as well. So it has a single pole, and this one will just be flat, and then it will start to attenuate at minus 20 dB per decade, and the corner frequency is set by this pole right here as 1 over R2 C2. Now the filters on the right-hand side are a little bit different because we have this 1 plus Z2 over Z1 response for them. They tend to go from unity gain to a higher gain, or from a higher gain to unity gain when the capacitor kicks in. So if we look at the first one, we can see that capacitor C1 is an open at low frequencies. And when C1 is an open, there's no current flowing through R1 and R2, and the output is then tied to the negative terminal of the op-amp, which with our virtual short is at potential Vn. And so at low frequency, the gain is 1, and then at high frequency, the capacitor becomes a short, and it just becomes the non-inverting configuration. So its frequency response looks like this. And this corner frequency here, which is set by the pole, will be 1 over R1 C1. And then the bottom one is the opposite. It starts at a gain of 1 plus R2 over R1, and then at higher frequencies, capacitor C2 becomes short, and it ties the output to the negative terminal of the op-amp, which is at a potential of Vn, and so the gain becomes unity at high frequencies. And so we see a Bode response that looks like this. And the pole, which is right here, frequency is going to be 1 over R2 C2. Okay, and then using these, we can design filters that have all kinds of interesting frequency responses. So let's take a look at, let me erase these. Let's take a look at this filter right here. And so it, when you look at it, has this step-up type response, looks very similar to the one shown in this circuit right here. Except this one always goes from 0 dB up to the higher gain, And then this one right here appears to be starting at 20 dB. So that's not actually what that circuit does. So let's go ahead and sketch in the one that we know that we can get. It starts at 0 dB, and it'll step up to 20 dB, and then it'll flatten out like this. And so then the question is, what other filter do I need so that I can add it to this orange curve to get the black curve? Right? So I'm going to draw that one in black. And so what we need is we need one that has this response right here, has a corner frequency here that brings the gain down. And then its gain needs to be 20 dB in this region, right in here, so that when you sum it with the 0 dB, it falls along the black curve. And then we would like for this curve to remain flat for all frequencies, all the high frequencies, so that at these higher frequencies, right in here, one stage has a gain of 20 dB, the other stage has a gain of 20 dB, and these sum up to the 40 dB that you see here. And then over here, we have 20 dB plus 0 dB, which is the gain of the black curve in this region. And then we can see that at this corner right here, one of the stages has a gain of 0 dB, the other one has a gain of 0 dB, and so that's exactly what the black curve is at. So this consists of two filters. And one is a high-pass filter, and the other one is a step-up kind of response filter. So if we scroll up here, we can see that we need a filter like this one, and we need a filter like that one. All right, so what I'm going to do is I'm just going to take both of them right here. I'm going to copy these. I'm going to paste them in here. So these are the two circuits that we need to cascade in order to get this response. And so the only thing that we need to do is we need to figure out what the component values are going to be. And so if we look back at our Bode response, we see that the bandpass gain for the red filter should be 20 dB in the bandpass. And so what we would like is we would like for R2 over R1 to be equal to 10. And so we can choose values for R2 and R1. And here we could choose, say, 10 kilo ohms for R2. We could choose 1 kilo ohm for R1, and then we would get a gain of 10 in the midband, which is what we are interested in. Okay? And then we just need to choose the value for C1 that will give us a corner at 10 radians per second. And so that corner frequency is 1 over R1C1. So we know that 1 over R1C1 should be equal to 10 radians per second. Right? And so C1 should be equal to 1 over, and then R1 we have chosen to be 1 kilo ohm times 10 radians per second. And so that is 10 to the 4. So it's 10 to the minus 4 farads, which is 100 microfarads. All right, for the right-hand circuit, we would like to have a mid-band gain of also 20 dB. So let's change colors here so we can see that here the gain is also 20 dB. Right? So we would like 1 plus, and let's renumber these for our circuit. We're going to call this one R4, we call this one R3. And so we would like 1 over R4 plus 1 plus R4 over R3 to be equal to 10. So R4 over R3 should be equal to 9. And so we could choose R4 to be 90 kilo ohms and R3 to be equal to 10 kilo ohms, and we would get that response. And then finally, we would like our corner frequency at 10K, right there, to be 1 over, and in this case, it is R3C3. Call this. Okay, so we'd like 1 over R3C3 to be equal to 10 kiloradians per second. And so C3 should be equal to 1 over, and we've chosen R3 to be 10 kilo ohms. So we have 10 kilo ohms times 10 kiloradians per second. So that's 1 over 10 to the 8, right? Which is 10 to the minus 8, which is 10 nanofarads. And so that finishes our design, and the only decision we still need to make is what order to cascade these two in. And because the non-inverting configuration has the high input impedance, we should use this stage first, and then hook the output of this stage into the input of the second stage. So the overall circuit will look like this. We have our non-inverting configuration, this is C3, which is 10 nanofarads, followed by a 10 kilo ohm resistor, followed by a 90 kilo ohm resistor, and this right here will be the input to our filter. And we cascade this with the inverting configuration, and we've chosen 100 microfarad capacitor, pretty large capacitor, and we have a 1 kilo ohm resistor. Now, if we wanted to make that capacitor value smaller, we could replace the 1 kilo ohm resistor with a 10 kilo ohm resistor, but then we'd have to also replace R2 with a 100 kilo ohm resistor. And then that goes into the second stage. This is our output for the circuit, and this is the 10 kilo ohm resistor, and that finalizes the design. Okay, so to review, we need to recognize the different shapes that we have available to us to easily design using these circuits, which we've covered in class. So we have 4 different circuits. We have a high pass and a low pass, and then a step up and a step down response available to us. And the key here is to be able to understand how these, at least 2 of these filter stages, will add up to give us the response shown by the black curve. And so we have identified that we can use the step up response in here to get this shape. And then we also need a high pass filter that has a gain of 20 right in here to give us that profile at the low frequencies. And those 2 curves added up give us the black curve shown in the graph. And then we can sketch our design, which I've copied and pasted from above, and then we just need to determine what capacitor value gives us the corner frequencies that we're interested in. And in both cases, we have looked at this pole frequency here in the denominator, okay, which told us where this corner is, and it told us where this corner is. And so we solve for those component values, and then we can sketch our final filter design.